T is not invertible, you understand this as meaning the free image. But preferably you should not write it. So I will really make an effort not to write T inverse, because T inverse in principle means the inverse of T. T may not be invertible. Nonetheless, whatever we have done here makes sense, because what I really do is I take a set in the image, and then I take its free image by use of T. So this is T inverse of A has a very clear meaning. It means all the elements in X such that T of X belongs to A. So I think that we should, and I'm really sorry that I use this, I shouldn't be sloppy. So for those of you that took pictures, please take another picture. And I hope that you will destroy the others. Yeah. So I've already removed those inverses from there. So what I really mean is take free image, but you cannot say T inverse. And you should. You shouldn't, and I shouldn't have. So okay, so there should not be a confusion here. We are not doing inverses. Nowhere here we are doing inverses. We are just doing free images of maps, or of sets by means of maps. So, okay. So I really hope that this is clarified now. And I leave that. I want to leave this definition nonetheless because it's useful to study. And let me write down a question. Suppose that a map T between two spaces, two sets if you wish, is given. And I also know that X prime comes equipped with a sigma algebra. So A prime is a sigma algebra on X prime. My question is there a smallest sigma algebra on column A on X such that T is a prime measurable? So the book has this dash here. I may write it or I may not write it. Maybe I don't write it, and it's too many lines on the blackboard. Okay. So you understand the question? I have a map between two sets, and on the target one I have a sigma algebra. Does there exist a smallest sigma algebra on the domain such that T becomes measurable with respect to these two sigma algebras? So now if I want to make it easy and I remove this one, is there a sigma algebra on X such that T is a prime measurable? Any at all? Can you think of one? So think about what it means for my map to be measurable. It would mean that whenever I take a set from X prime, from A prime, the sigma algebra here, the free image should land into this sigma algebra on X that you want to think of. Can you think of one? Yes? The power set of X would be one, yes. So if I remove this, then the answer is yes. A equals P of X, power set of X, set of X would do. Because free image will be a subset of X, so it belongs to the power set of X. Yeah? So would do, then T is P of X, A prime, measurable in a very trivial way. The thing is that, when you take the power set so that it's all possible subsets of X, then you don't have much information about the map here at all. So I would say not very interesting. So I'm interested in other ones, and because I may have potentially others, I'm interested in the smallest possible one, meaning one that would contain all the other sigma algebras for which which this would work. So that is why it really makes sense to add this smallest. Yeah. So now the answer is, this yes here refers to without smallest. Okay, so now, is there a smallest sigma algebra on A such that T is A prime measurable? So the answer is yes. So I write it in pink because it refers to this new question. And this is the so-called sigma algebra generated by T, which is by definition, well, if you want symbolically to write, it's the pre-image of A prime. Yeah. So I want to point out that this is example 3.3, so that's in chapter 3, and it's the 7th of them. And I'm wondering, have you covered this, or have you looked at it yourself? If not, please do. So it is shown in the book that this is indeed a sigma algebra on X. So if you want to expand it out, these are sets of the form pre-image of A prime such that A prime belongs to A prime. So what is shown in this example is that this is a sigma algebra on X. So now what we want to show, so the claim is that, and it's very easy to see, the claim is that this sigma of T is a sigma algebra on X, so that T is a sigma algebra, so that T is sigma T A prime measurable. That's one thing. And then the second thing is that it's the smallest sigma algebra with this property, so I write it long. If A is a sigma algebra on X such that T is A prime measurable, then A contains this sigma of T. And I forgot if the book is contains with contain and equal, or is this how we use it, or without? Okay, so without it also could mean equal. Okay, good. Okay, so you see that will make it the smallest sigma algebra with respect to which T is now measurable when you have A prime on the target space. So there are two things, and once we understand this, I think we are ready for more complicated setting. So let's try to verify these things. So once again, this sigma prime of T is this. So it's the collection of pre-images of sets in A prime by means of T. I want to understand, I will not prove that it's a sigma algebra. That's part of the example 3.3 in the book. So the fact that this is a sigma algebra, I would say, see the book. But I would like to understand together why T is sigma T A prime measurable. So show T is sigma T A prime measurable. There's not much to show, right? It's almost like writing down the obvious. So to show that this is measurable, so we'll have to let A prime in A prime, and we have to show that pre-image of A prime is in sigma T. That's my sigma algebra. Is there anything to argue? Sigma T consists of pre-images of things in A prime. That's just the definition of sigma T. So, clear. Yes? Yeah, okay, so by its very own definition, T becomes measurable with respect to the sigma algebra. And so now you can see why this should really be the smallest, because it contains all that it should and nothing else, right? You should always have the pre algebra on X such that T is a prime, yes, measurable. So what we want is that this A contains the sigma algebra generated by T. And by the way, this I keep saying that, but I didn't tell you if you didn't read the example. This is a sigma algebra on X called the sigma algebra generated by T. So I keep calling it like that, but I didn't tell you that that's its name. Okay. So how can I prove such a thing? For example, so I know that A is a sigma algebra. I want to show that it contains a sigma algebra generated by T, which, by the way, I remind you again, this is this T inverse A such that T inverse of A prime belongs to A prime. So if I show, for example, that A contains all these sets, then I'm done, right? Okay, so let A prime in A prime want T inverse A prime belongs to A prime, right? Because then I'm showing that it contains everything from this set. Is this true? We are sort of writing the obvious on this blackboard all the time, right? This is the definition of the fact that T is A prime measurable. Whenever I take a set from A prime, pre-image of that by means of T is in, what am I saying? A. Yes. It's in A, right? So this is true since T is a prime measurable. Okay, but this means that whenever I take A prime in A prime, this set belongs to A. So that means that the whole right-hand side is contained in A, and that's what we wanted. It looks tricky because it's very, very simple. So sometimes very simple things look tricky, but it's just writing down the definition. So we are done again. I mean, this thing, it's okay. So there is a smallest sigma algebra on the domain such that T is measurable with respect to that when the sigma algebra on the target is given, and that is this sigma algebra generated by T. So now maybe we go to the definition in the book because he doesn't comment much on the previous one, so I hope that this will make it easy to understand. So if I have a whole collection of maps, so it's indexed over some index set I, be a family of maps. I don't care if it's countable or not, it doesn't matter. And these are maps defined, all of them, on the same space, and their domains might be their images might be different. So from same space X into measurable spaces. So the target space has a sigma algebra on it. So Xi equipped with sigma algebra AI. Then the smallest sigma algebra on X that makes all Ti measurable is in yellow sigma algebra generated by the family Ti I9, which by definition is the sigma algebra generated by the union of these families Ti inverse of a I and I. And it is called the sigma algebra generated by the family Ti. Okay, these are, so 3 images of things in here are subsets of X. So I can take the union of them all because they are all subsets of X. Why do I have to take the sigma algebra generated by them? I don't know if you encountered this already. If not, maybe you can start thinking about it. In general, the union of sigma algebras may not be a sigma algebra. So even though each individual here, these are sigma algebras, when you take the union, you may not get the sigma algebra. So you need to add more things to it. That's why we take the sigma algebra generated by. So here, this is the comment. Note, union of sigma algebras may not be sigma algebra. So, okay, here I wrote Ti inverse of AI. I could have written, and I don't know what, maybe that's what the book does, that's why I wrote it. I could have written, and it's the same thing. I could have written here, maybe it looks bad, that's why they don't do that in the book. So let me write it. Well, I could have written this sigma algebra generated by Ti. It looks shorter, but then you have sigma algebra union sigma algebra, so you may not like it. Perhaps that's why the book preferred to write like this, Ti inverse of AI. But again, it's not Ti inverse, it's free image. Free images of sets in AI. Yeah? So it makes sense to add this sigma here. The note refers to why do I have to take the sigma algebra generated by? Okay, so you see, it says definition, but it's actually not exactly a definition because it's telling you things that you should check. So this automatically implies that we should have checked before putting it down as a definition several things. So it is a sigma algebra because it's the sigma algebra generated by. But I need to check that the first thing, each Ti is sigma Ti AI measurable. Because it says the smallest sigma algebra that makes all Ti measurable is. So I need to know that it makes them measurable. Right? So each Ti, I need to check that for all I know. And the second thing is that it's the smallest one indeed. So if A is a sigma algebra on X such that Ti is A prime measurable for all I in I, then A contains this. I claim it's the smallest one. Yeah. So in fact the book says definition and lemma and gives it like that. So it's because before you say the smallest sigma algebra that makes all of them measurable is, then you should really check that it makes them all measurable and it's the smallest one in this problem. So I think that I feel confident that because you have gone through the case of one map, and if you understand that, you should be able to do this for several maps yourself. I don't want to do it, but think about it, why these two things are. It's again not difficult at all, it's just writing down what we should. Okay, so the next thing that I maybe want to do, let me write it here. Hope I don't need this definition again. It's about the notion of image measures. So let me write it down and then we'll comment on it. So let me should write A prime measurable, and the definition of that I just erased. Let mu be a measure on the first space. On XA, sorry. Define mu prime on A prime being an element of the sigma algebra A prime, to be in the following way. So let's see. I have my X A here, I have my X prime A prime here, and the map T that goes from one to the other. I take a subset here, A prime. Yes, A prime coming from the sigma algebra A prime. And what this theorem is telling me, I have a way of measuring sizes of sets in the sigma algebra A, right? I have a measure on the sigma algebra A, so I can measure the size of sets in the sigma algebra A. I want to construct or give a recipe for measuring size of sets from the sigma algebra A prime, given that I have a measurable map between these spaces. Can I do it? Well, so I have my set in A prime, I can transport it back into the sigma algebra A by pre-image, so this would be T inverse of A prime. Since T is measurable, this one, T inverse pre-image of A prime belongs to A, and I know how to measure sets in A. I use the measure mu. So this is how I do the recipe. This is mu of T inverse of A prime. Yeah. Now the claim is that then, where am I? Then mu prime is a measure on X prime A prime called the image measure of mu by T. So once again, I have a way of measuring sets. I have a measure on A, and I have a measurable map that takes me to another space. This gives rise to a recipe for measuring the size of sets in A prime if you do this. So the theorem says that this is a measure, right? That's the conclusion of the theorem. You have to prove you get a measure. I think that this is one of the theorems that is left to be discussed in the exercise session, but you can, of course, you're welcome to read it already from the book. And I want to point out that this is a very important construction in probability. You will encounter it at the too. So this is very important, especially in probability, but not only. Very important in probability. And I will say C block 2. The course MI in block 2, you will be talking about all sorts of such examples that arise like this. Especially when you consider this mu to be a probability measure. You will get a probability measure on the target space. Okay, so because this is all too abstract, I propose that we look at concrete examples of images of the Lebesgue measure by means of various measurable maps, or rather a special class of them. Some of which we have encountered already, like the translation map in RM. So I will photo. So I will say important examples of image measures so this would be transformations of Lebesgue measure. Okay, but to recall something from linear algebra. If A is an n by n matrix, then you can associate to it a map. It's going to be a linear map, in fact, a mapping, I can put it like that, T, that goes from Rn into Rn. So I'm taking n by n matrix, a mapping given by, I hear a sigh, that's because of linear algebra, Tx equals Ax for all x in Rn. So if x is a vector in Rn and you have an n by n matrix, you know how to multiply a matrix by a vector, right? This will look like this. And you will get a vector, right? So Tx, where x is in Rn, gives you another vector in Rn by means of this. Okay. But there is also a converse. So conversely, if T is a map from Rn to Rn and it's linear, then I can associate to it a matrix. And this matrix is constructed in the following way. I'm going to tell you what the columns of the matrix are. Well, you know, in Rn you have the so-called orthonormal bases. So E1, it's the vector with 1, 0, 0. In general, EI, it's the vector that has 1 just on the position I, and 0 else, right? And the last one is En with 1 on the last position. So then the columns of the matrix A are T applied to these vectors. So T of U1, it's the first column of A, and so on. I'm telling you the last column is TEN, so this is the nth column of A. Right, so T1 will be an n-dimensional vector that you put it as the first column of A, and so on, right? So what I'm trying to say here is that there is a one-to-one correspondence between, so A, n by n matrix. It's in one-to-one correspondence with mappings T from Rn to Rn, such that, in fact, Tx is equal to Ax for all x in Rn. The point of all of this introduction being that the book jumps right into saying, let T be n by n matrix, and then he refers to it as a map. So I'm trying to say that we will not distinguish between a linear map T from Rn to Rn and its associated matrix. So when you have an n by n matrix, I'm going to think of it as a map, and when I have a map, I'm going to think of it as a matrix, and I call them the same, typically T. Okay, good. So now, there are some special matrices, n by n matrices. You may have encountered them, I don't know. Let's see. They are called orthogonal matrices. So it says, so definition, an n by n matrix T is called orthogonal if the transpose of T multiplied by T gives you the identity n by n matrix. So this is the matrix, you know, which has 1 on the main diagonal and 0 else. Yeah, so you can see right away using linear algebra that any orthogonal matrix is invertible, and the determinant is, so P orthogonal implies T invertible, and determinant of T is, yes, plus or minus 1, right? Because the determinant of this will be determinant of T squared, which is equal to 1, so that is determinant of T plus or minus 1. Yes. An example of an orthogonal matrix is the following. If you take theta between 0 and 2 pi, and I'm writing down the following matrix: cosine theta minus sine theta, cosine theta. Have you encountered this one? This matrix corresponds to what kind of operation on R2? You haven't encountered it? I make a picture and then you tell. So if I take a vector x in Rn and I apply Tx to it in R2, and I apply Tx to it, where do I go? It rotates by angle theta. So this is the matrix corresponding to, this will be Tx and this is theta. So this corresponds to rotation by theta. So maybe this will also help you understand the observation in the book that orthogonal matrices preserve length. So you can see that the length, the Euclidean distance, so the length of the vector Tx is equal to the vector, the norm of x for all x here in R2. But it's generally true for orthogonal matrices. We don't need that because we cannot understand everything that's in the book. That's due to the fact that some things you will learn in block 2. But this is good enough for us to understand the following thing. So the observation is, I'll do the down remark. Any orthogonal matrix preserves length. So that means that norm Tx is equal to norm x for all x in Rn, and it's continuous. Any orthogonal matrix is continuous. This sounds stupid, but as I said, we think of matrices as being the same thing as the linear operator, a linear mapping associated, so then it makes sense to say that it's continuous and hence measurable. So this is why these ones are important for us. Did you have a question or something not clear? You could read any preserves. This one, yeah, I should be more careful on that. Preserves. Yeah, maybe that's better. Okay, so here is a theorem in the book. I think it's called 7.3 in my notes. I hope it's correct. It says if T is an orthogonal map from Rn to Rn, if you start in this theorem here, with your measure mu here in your bag, and you apply to it this orthogonal map, you end up with a new measure. It's going to be a measure on Rn, and actually you end up with Lebesgue measure again. So then T of lambda n, this is a notation for the image measure of lambda n by T. So that's the construction that we refer to in that theorem, that measure mu prime is actually equal to lambda n. Yeah, so the result of applying, of taking the image measure of Lebesgue under an orthogonal transformation, it's Lebesgue measure on Rn. Of course, this maybe I should make it in color so we understand which Rn and which Lebesgue is it. If I can find the colors in color. I see one, and I see two. That's good. So this is the first, yeah, it's on here. And the end result is on here. Yeah, so I'm putting the image measure sits on the target space. Okay, unfortunately we cannot talk about the proof of this because in order to conclude, so here you have a measure, here you have another measure, you have to have a way of telling when two measures are equal other than just computing their value on individual sets. That is the so-called uniqueness theorem for measures, and we decided to leave this for block 2. So for the proof of it, you will have to wait until block 2. But I think that I have time to do more than just this. So you see orthogonal matrices are always invertible and they have determinant plus or minus 1. What about if I would like to apply to Lebesgue measure another invertible matrix, but not necessarily orthogonal? So more generally, for any invertible matrix S, we have the following, and this is theorem 710 in the book, which says S n by n invertible matrix. He has a notation in there, but we don't necessarily need it, so it's the so-called GLN, general linear group of order n, we don't care. So it's just an invertible matrix. Then the result of starting with the Lebesgue measure and taking its image through S is a scaling of the Lebesgue measure by means of 1 over the determinant of this matrix, and I have to take absolute value because I need a measure, so that I need to take positive values. Yeah? So the image measure, this is how you read. The image measure of Lebesgue under the invertible matrix or the invertible map. S is a scaling of the Lebesgue by means of this factor, 1 over the determinant. I think maybe if you allow me, I take 2 minutes to give you the idea of the proof, because we cannot, again, like how many times did I say we cannot do the general thing? But let's look at it so that you understand where this scaling factor is coming from. So consider, and I don't think he does it in the book, he just gives you the proof. Consider the special case when S is a diagonal matrix, so it has lambda 1, lambda 2, and so on, lambda n on the diagonal, 0 rest. And I'm also assuming that this lambda I, so it should be invertible, so they should not be 0, but I'm taking them to be strictly positive, all of them, because I don't want to have to deal with the absolute value here. Now, what's the determinant of S if S is diagonal? Yes? All of you, okay. Product of the diagonal entries, so it's product of lambda I from 1 to n, yes? So then what we want to show here, so I want to somehow convince myself that if I do the image measure of Lebesgue by means of S, I get exactly this, 1 over lambda 1 times lambda n. Oh God, why did I choose lambdas? They look like Lebesgue. You should have told me. Alpha. Alpha 1, alpha 2, alpha n. There is a reason not to do things in the last minute, because that's what they come out. So. But I just want to finish with this, and then we move on to the next section. So I'll just give you the brief idea. So here we are. So this image measure is a measure, right? And it's because that's what the theorem tells us. It's a measure. So I can use it to measure boxes. So if I do this measure applied to a box, A1, B1, AN, BN, what do I get? Well, by the definition of this image measure, S on lambda n, which is given here, right? So this is I didn't tell you the essential. That this measure is denoted by T of mu, so I'm using all the time something of lambda n. So this image measure denoted by T of mu. So this mu prime that we construct here is T of mu. So now we can see the definition of it. It will be, so if my map T is S and mu is the vec measure, then you get the vec measure of a pre-image of the box by means of S. So this is lambda n of pre-image. So I want you to think about what this pre-image is, and if you think about it, you will realize that this is another box, but it has different size or shape, whatever you want to call it. It's the scaling down of the endpoints. So it looks like this. AN alpha n, BN alpha n. This is what the pre-image by means of S of this box is. It's a new box, but shrunk. And the Lebesgue measure of such a box, right, then this is B1 minus A1 over alpha 1 times Bn minus An over alpha n. But that is exactly lambda n of the box, A1, B1, An, Bn, divided by precisely the product of the alphas, which is the determinant of S. Yeah, so what we can do is to show that this image measure is indeed a scaling of the Lebesgue by means of determinant of S on boxes. And then you need that result that tells you if two measures agree on boxes, because boxes generate the whole sigma algebra, they will agree everywhere. So that's again this uniqueness theorem that we don't have. But this is good enough to conclude result. I just wanted to somehow show you where this determinant on the bottom comes up and why do you get